Hi, this video is an introduction to our paper, Fast, High-Quality Hierarchical Depth Map Super Resolution. I'm Igor Qiao, a research associate in the University of Bath. This work was done in collaboration with Li Chengjiao from Xidian University and Wenbin Li, Christian Richard, and Darren Kosker, all from the University of Bath. Depth acquisition, at the core aspect of stereo vision, is of great significance. Microsoft's Kinect sensor is one of the most popular ways to obtain depth information. Despite their popularity, the low resolution of the depth maps obtained from RGBD sensors is a drawback of present devices. Depth map super resolution, under the guidance of the corresponding high-resolution RGB image, is an attractive approach to alleviate this issue. However, edge preservation is challenging. Artifacts such as depth confusion and blurring are easily introduced near boundaries. In view of this, we first propose a method for fast, high-quality hierarchical depth map super resolution. In the second part of this paper, we extend this basic HDS model to a classification-based hierarchical depth map super resolution model. Here is the overview of our two methods. In our basic HDS model, instead of one-step upsampling, a hierarchical image pyramid strategy is adopted to reduce the interpolating errors. To improve the upsampled depth quality, we further introduce a feature-based bilateral filtering into the model. To accelerate the process, we perform filtering only near depth boundaries and through matrix operations. In the upgraded CHDS model, a context-adaptive classification strategy is first introduced to reduce the contributions of invalid neighbors to the interpolation. Then the interpolation is implemented via a joint trilateral filtering which includes the classification result. The hierarchical image pyramid strategy generally consists of 3 steps. Take the 4 times super resolution as an example. First, the RGB image is downsampled by a factor of 2 in each layer to get the low-resolution RGB images. Then from the last layer, we map the low-resolution depth map to the high-resolution grid in the layer above to get the sparse depth map. Finally, the sparse depth map is interpolated by joint bilateral upsampling under the guidance of the RGB image in the same layer. Repeat the second and the third steps until the target high-resolution depth map is generated. To improve the quality of the upsampled depth maps, a convolutional downsampling together with the VGG16 network is used to extract rich features. This figure shows the feature extraction process under a 16 times super resolution scale. The multi-layer feature extraction based on the proposed multi-layer convolutional downsampling is indicated by blue lines, while the shallow feature extraction via VGG16 is indicated by pink lines. With the extracted context maps, the basic joint bilateral filter can be promoted to a feature-based bilateral filter to achieve the feature-based hierarchical depth map super resolution. To accelerate the performance, we propose a concise mechanism of our method through both depth boundary detection and matrix computation. We first detect edges in the depth maps so that bilateral filtering is performed only in these regions. In an intermediate bilinear upsampled depth map D star, a pixel P will be treated as a boundary point if the depth range within this window NP is larger than a threshold. The rest regions are filled with the corresponding regions in the intermediate upsampled depth map D star. That is, we accelerate the program by reducing the number of interpolating operations. We also try to accelerate the process by converting pixel-by-pixel calculations into parallel matrix computations. We first expand the bilateral filtering function and convert this expression into coordinate form. Then, by shifting the image up, down, left, and right, we simultaneously interpolate the whole image. To achieve sharp and clear depth edges, we upgrade the basic HDS model to a classification-based HDS model, in which a context-aware triliteral filter reduces the contributions of unreliable neighbors to the current missing depth location. Firstly, we classify the neighboring non-blank pixels of a to-be interpolated point into different classes according to the depth. Secondly, with the aid of the RGB image, probabilities of a current point belongs to each classes are calculated according to the Gaussian weights from the corresponding RGB points, where n presents the total number of classes. If the maximum probability of P is larger than a threshold, the current point is assigned to this class. Lastly, we construct a joint triliteral filter by combining the classification result with the high-resolution RGB image and the to-be upsampled depth map. Hence, the upgraded CHDS model is achieved. Note that the high-resolution RGB image can also be replaced by the convolutional feature maps to construct a feature-based triliteral filter, creating a feature-used and classification-based hierarchical depth map super-resolution model. We conduct our experiments on Midbury 2005, 2006, and 2014, and extensively compare our four methods, the basic HDS, FHDS, CHDS, and FCHDS, with state-of-the-art approaches. We use both mean square error and bad pixel rate error for quantitative evaluations. Bad pixels are those whose values deviates from the ground truth by more than one disparity level. Quantitative evaluations for different super-resolution scales are provided in this table. We compare the proposed methods with state-of-the-art interpolation, optimization, and learning-based methods. We use mean square error discontinuity and bad pixel rate discontinuity to evaluate the performance near discontinuities. In summary, the proposed methods are able to generate high-quality upsampled depth maps in both visual and quantitative evaluations. They demonstrate a significant improvement for the large-scale case over the current state-of-the-art approaches. FHDS provides visually best results due to the use of extracted shallow and multi-layer feature maps. CHDS particularly shows the best bad pixel rate measurement with fairly low mean square error values guaranteed for most of the trials. FCHDS takes advantage of FHDS and CHDS, yields the best result by taking both visual comparison and quantitative analysis into account. In terms of runtime, the proposed methods outperform most of the baselines. The basic HDS model achieves 7.6 Hz using parallel computation on CPU. In conclusion, we propose a fast and high-quality hierarchical depth map super-resolution method in this paper. We further upgrade this basic method to a classification-based hierarchical depth map super-resolution method. Experiments verify the superiority of both the basic method and the upgraded method compared with state-of-the-art approaches, especially in the case of large scale. The program is stable, training-free, and easy to implement, with runtimes exceed other methods to the best of our knowledge. The proposed method is also applicable to depth map inputting and can be applied on other types of fusion data processing, such as RGBT data. Like most methods, our method is insensitive to information which are easy to lose in low-resolution depth maps, like thin lines. Our future work is to find a linear correspondence between the RGB image and the depth map to retrieve those missing information. Thanks for listening.